Welcome to The Explainer. Today, we're diving into a really fascinating engineering quest. We're going to explore exactly what it takes to completely retrofit a highly technical medical manufacturing machine. Specifically, we're looking at an incredible project developed by Waqas Javad for a company called Senzo Medical. Our mission today is to uncover how you take a legacy system that relied way too heavily on manual operation and completely modernize it using industrial automation. Because the core challenge here was exactly this. How do you teach an old, purely mechanical machine to think, and more importantly, to act with strict medical-grade precision? We aren't just talking about slapping a motor on something to make it spin. We're talking about giving a digital brain to a physical system so that it operates flawlessly every single time. It's like a giant puzzle, and honestly, the way they solved it is absolutely brilliant.
Section 1. The need for automation. The inciting incident.
So historically, this BMC, or biomedical component machine, was operated manually, or at best, semi-manually. And in medical manufacturing, that is a massive bottleneck. The old setup was plagued by human error, inconsistent product quality, and uncontrolled jerky motion that was causing severe mechanical stress on the machine itself. So what was the goal? They wanted a fully automated PLC-controlled reality that could offer high-speed accuracy, total repeatability, and perfectly smooth motion to actually protect the hardware.
Section 2. Anatomy of the BMC. Breaking down the machine. To successfully automate this thing, we have to hit some incredibly stringent engineering specs across two primary mechanical subsystems. First up, you have the upper circular track for rotational motion. This track maxes out at 150 RPM, but it demands a literal microscopic 0.1 degree resolution. Then you have the outer vertical mechanism handling linear motion. That requires a 500 millimeter stroke with 1 millimeter resolution, all while handling an 80 Newton load. To put that into perspective, balancing that kind of raw speed with that level of precision is exactly where the magic happens in this build. Section 3. The hardware brain. Equipping the machine to think.
Okay, so the absolute superstar of this new setup is the Programmable Logic Controller, or PLC. A Siemens PLC was chosen to act as the central processing hub, basically the conductor of the orchestra for the entire system. It aggressively pulls real-time signals from all these different sensors, instantly calculating and then dispatching the exact logic required to drive the servos flawlessly.
And backing up that Siemens PLC is one seriously robust hardware toolkit. The machine was upgraded with high-torque servo motors that feature integrated encoders to give that crucial real-time positional feedback. They also threw in proximity sensors, redundant limit switches to absolutely prevent any accidental overtravel, and safety relays. And, because this is an unpredictable industrial environment, the whole shebang was housed in an IP54 rated control box. That basically means it's tough enough to shrug off dirt, dust, and water splashes without breaking a sweat.
Section 4. Coding precise motion. Software and PC integration.
So how does all this hardware actually communicate? Well, it creates this beautifully streamlined flow of data. First, an operator inputs a command via the PC interface, which has a command line set up alongside a simplified graphical overlay. That data then travels instantly over an Ethernet connection using the Modbus TCP protocol. The PLC takes that data, processes the logic, and dispatches the exact power instructions down to the servo motors so they can execute the physical movement.
Now, right at step 3 of that process, the PLC leverages something called PID control loops to manage the motion profiles. If you think about it, instead of abrupt, jerky starts and stops, these PID loops act like a highly advanced cruise control. They dynamically calculate the exact power being delivered to the motors. This guarantees incredibly smooth acceleration and deceleration, ensuring the machine hits its exact target without oscillating, overshooting, or causing any violent mechanical stress.
Waqas Javad, the developer behind all this, noted that the key parameters, acceleration, position, and velocity, were made configurable by the operator, with all adjustments logged for traceability. This really highlights how flexible the new software is. An operator can literally adjust acceleration or velocity on the fly. If a process suddenly needs a slower rotation to protect a fragile medical component, they just type it into the PC. Plus, the system includes Python IoT testing scripts, and absolutely every single parameter change, command, and fault is recorded in a system event log. In the medical manufacturing world, that level of traceability isn't just a bonus feature, it's strictly required.
Section 5. Overcoming engineering hurdles. The climax of the build.
As anyone in engineering knows, theory is great until it meets reality, right? Integrating this theoretical software into physical legacy machinery presented three major hurdles. First, they had to attach brand new servo motors to old lead screws. They solved this by designing custom mounting brackets and couplings to preserve the machine's core design. Second, they ran into mechanical resonance, basically unwanted, damaging vibrations at certain speeds. They fought this by deeply fine-tuning those PID loops we just talked about and adding physical mechanical dampers. Finally, industrial environments are notoriously noisy electrically, which can really mess with Ethernet signals. They mitigated this by using heavily shielded cables and programming robust error checking directly into the PLC.
Section 6. The final results. A triumphant automated reality.
So, did all this hard work pay off? Well, the results of the commissioning phase absolutely speak for themselves. The newly automated system achieved a staggering 96.7% accuracy rate in testing. By simply removing the unpredictable human element and relying on those PLC-driven servo motors, the overall consistency of the manufacturing process just skyrocketed.
And check this out. Before the machine can even start its actual work, it has to find its absolute starting position, a process called homing. Thanks to the new limit switches and those high-torque servos, the entire homing sequence for both axes is completed in a lightning-fast 4 seconds.
What about lag? Well, when the operator clicks a button on their PC, the system responds almost instantly. The communication latency between the PC interface and the Siemens PLC stayed under 50 milliseconds. That is a near instantaneous response to operator commands, which really proves the absolute stability of that Ethernet Modbus TCP connection.
But the ultimate triumph here, the real showstopper, was the positional accuracy. The machine consistently maintained its strict 0.1 degree positional resolution, even while operating at its absolute maximum rotational speed of 150 RPM. And it did all of that without a single mechanical overshoot. They perfectly balanced high-speed production throughput with the incredibly strict mechanical safety limits required by Sensor Medical. It's a massive engineering triumph.
We've seen how smart engineering, some custom brackets, and a rock-solid PLC can take an aging, manual machine and totally transform it into a highly precise, data-logging, medical-grade powerhouse. It really makes you think about the possibilities, right? As industrial automation continues to revolutionize these rigid legacy systems, I want to leave you with this. What manual, outdated process in your own industry is just sitting there, waiting for its digital brain?